Unifesp cada vez mais perto de você. São 2 canais oficiais no YouTube com conteúdos exclusivos. Inscreva-se nos canais e não perca nada. @Unifesp Oficial e @Unifesp.alvivo.
Hi everyone, my name is Walter Lima. I am a professor at Federal University of São Paulo, and I am also leading an artificial cognitive system research group. It's an honor to welcome Antonio Lieto. Antonio Lieto is a tenure-track senior researcher and assistant professor in computer science at the Department of Computer Science of the University of Turin, Italy. He also a research associate at Institute in Palermo, Italy, in Cognitivo Robotic and Social Sensing Lab. In the past years, he have been visiting research at University of Haifa, Israel, at the Carnegie Mellon University, US, Department of Psychology and School of Computer Science, and in Lund University, Sweden, Department of Cognitive Science. In 2018, he was a recipient of the Outstanding BICA Research Award, an international recognition for your research on cognitive artificial systems and cognitive architectures from the BICA Society. In 2020, he was awarded the ECM Distinguished Speaker status from Association for Computing Machinery. Professor Lieto was invited to participate in this webinar due to his innovative work as researcher in the field of robotics. My first contact with the Professor Lieto works was through your book, Cognitive Design for Artificial Minds. I have adopted this book in my class about artificial cognitive systems. This book here. In your lecture, Lieto explained how the human mind works and how we can build artificial systems that display intelligent behavior. These two questions lie at the core of the cognitive science and artificial intelligence. While they have been treated independently from each other in the recent past, Lieto argues here that two fields have common history, and that it's time to reboot the bridging between cognitive science and AI. Also with us in this webinar, Wellington Pacheco. He was a student in the Disciplinary Professional Master's Program in Technology Innovation at the Federal University of São Paulo, when he produced the dissertation entitled Towards an Artificial Cognitive Model to Assist Caregivers in Decision-Making for Persons Living with Dementia. The scripts for webinar will be first a lecture by Professor Lieto. So we will open to debate with directing question to Professor Lieto by Wellington Pacheco. Then we will open of questions from the audience. So please send questions to Lieto through this chat on YouTube. Having said that, I am a pleasure to invite Professor Lieto to give his lecture entitled Cognitive Design for Artificial Minds. Welcome, Professor Lieto.
Yeah, so thank you very much for the very kind introduction, for the invitation. It's really a pleasure for me being here. Well, the topic of, actually, as you mentioned, the title of my lecture is exactly the title of the book that you were mentioning previously, so Cognitive Design for Artificial Minds. So I will try to touch some of the key elements of the book, which addresses some foundational issues in, let's say, in AI research, current AI research, in particular, and also in the area of cognitive modeling. So, in particular, the driving questions of the book and also of my research are the following ones. So, what characterize biologically or cognitively inspired AI systems? What are examples of biologically or cognitively inspired AI system? How such system differ from standard AI system? How can biologically or cognitively inspired AI system be used? How they can be evaluated and compared? And how this class of system, this kind of approach, can help to develop the next generation of AI system going, let's say, beyond the deep learning. So the framework in which we are is the following one, which is actually a logical framework that was developed by the cybernetics. So the idea is to build artificial system by taking inspiration from a natural system taken as a reference, as a source of inspiration. And this is, let's say, the first part of the story. The second part of the story is also try to use the output, let's say, of this system in order to better explain or to better understand some hidden mechanisms that were not really, let's say, available to our intellectual capability ex ante, so before, let's say, the implementation of such system. So the point is not only to have this kind of, let's say, first arrow, the inspiration arrow, but also trying to use these tools in order to explain some hidden mechanism of our brain and of our mind. So this is the overall idea of using a biologically or a cognitively inspired approach to the design of artificial intelligent system. So, but here, if we focus on the second arrow, let's say on the arrow that requires the explanation, a sort of reverse inference, we have some additional questions. So, for example, when a biologically or a cognitively inspired computational system or architecture has an explanatory power with respect to a natural system that has been taken as a source of inspiration. And finally, which are the requirements that we should consider in order to design, let's say, an artificial model that we can define as a computational model of cognition having this sort of explanatory power that I was talking about before. Now, in order to answer to these questions, in the book, I introduced the distinction between functionalist approaches to the design of AI system versus structuralist approaches. Now, in a nutshell, the main difference is the following one. So, functionalist artificial systems are systems that mimic, let's say, only the functionality of a corresponding natural system. So, for example, are systems that are able to deal with the same input-output specification, okay, and that have just a very weak resemblance in terms of, let's say, the mechanism and in terms of how the artificial system has been built with respect to how the natural system that is able to perform the same function is built. Okay, so there is a sort of weak equivalence here, or a surface resemblance between the natural system taken as a source of inspiration and the let's say, implemented artificial system. This is for the functional side. For the structuralist side, what we have when we, let's say, build a system by using this design approach is a much more constrained resemblance of the internal components of the artificial system that is going to be used and of their working mechanism. Okay, so components and mechanism of an artificial system based on the structuralist assumption are much more constrained. It means that they resemble very much what we know about we as a natural system are built, and what are the mechanism that we use in order to perform a certain kind of function. Okay, so here the importance is not only the fact that we are able to provide the same kind of output, let's say, when we face the same kind of input with respect to the natural system, but it is important that we also the way in which this output is produced, and the way in which this output is produced is much more faithful, let's say, with respect to what we know about how our brain or our mind work in order to perform the same kind of cognitive function. Now, it is possible to see these two approaches as two elements of a continuum, in the sense that between a pure functionalistic approach and a pure structuralistic approach, we can have in the middle different kinds of models of, let's say, structuralist or more, let's say, functionalist that can have different kind of explanation. They can have different kind of explanatory power. And in the book, I mean, I go into the details by telling exactly, let's say, which kind of explanation we can attribute, for example, to different types of structuralist account. Of course, let's say one thing that I stress in the book is that when we want to build a complex system, we always use a mix of, let's say, functionalist component and structuralist components, okay? Because it is not possible, of course, to reproduce completely, let's say, an entire, let's say, human being if we are taken as a source of inspiration. So this is an important element. So, and in general, another important element that I stress in the book is that it is possible to build structural models of cognition, so systems, computational systems that have an explanatory power with respect to, let's say, how a given function is provided in the brain or in our mind, by using different kinds of, let's say, levels of abstraction in our modeling focus, and therefore also by using different kind of AI approaches. Okay, so this is a classical example that I do when I want to provide, let's say, the function of natural language understanding. I can focus at the level of the different processes that this overall function includes. So syntax processing, morphological processing, lexical processing, and so on and so forth. And this means that I can eventually, for example, prefer the adoption of some class of, let's say, symbolic or hybrid models, for example, probabilistic ones. Or if I'm interested in, let's say, the biophysical plausibility of processes which, let's say, are underneath these processes, well, I may use, for example, different kinds of emergentist based approaches, like the connectionist method, but also connectionist approaches, but also, for example, dynamical system approaches, and so on and so forth. The first, let's say, important message here is that we may build explanatory models, so structurally valid models, in different ways. Okay, so it is not just, it is not true that, for example, if we use a neural model to curve, we are always more, let's say, closer to the biological plausibility of, for example, other kind of models. And let's say another let's say aspect of this element is that cognitive artificial systems that are built with this kind of structuralist approach, they can actually provide, they can play the role of a sort of computational experiment. Okay, so they can provide results that can be useful for refining or rethinking some theoretical aspects of the natural inspiring system that was taken initially as a source inspiration. Now, if we look at the history of artificial intelligence, we see that starting from the beginning and also before the artificial intelligence workshop in Dartmouth, okay, with cybernetics, as I was mentioning, there was this tendency of, let's say, building AI system by strongly taking into account a cognitive or a biological inspiration. Okay, so based on, as I was mentioning, on the level of abstraction that we were considering when building this kind of models. But let's say current AI, on the other hand, focused on a completely different approach. So the idea was that one of trying to, let's say, focus on the improvement of very narrow task, even without considering, or like let's say we are like we see nowadays in AI, without considering any kind of biological or cognitive aspiration. So in particular, if we look at the modern successful AI systems, both in the let's say the field of symbolic system, but also in connectionist system, we may say that they are functional systems. Okay, so they have been built by using a functionalist design approach. This means that they don't have any kind of explanatory role with respect, for example, to how we I don't know deal with the problem of question answering, or how we play the game of Go, or let's say how we, for example, discover the structure of proteins. This is the result obtained by AlphaFold, or how we generate text, how we generate story, how we deal with our language capabilities. Okay, so all these systems are functional systems, so they have nothing to tell us about the way in which we are able to perform the same kind of functions. In other words, they don't have any kind of explanatory role. Okay, that because they have not been built by using a let's say a biological or a cognitively inspired approach. And indeed, we can have, let's say, a sort of proof of concept of what I'm saying if we look not just at the let's say successes of these systems in terms of performance, but if we look at the errors. So these errors are really strange for humans. Okay, for example, this is the IBM Watson system that was developed by IBM and that was able to beat the champion of the Jeopardy play. There is a very funny video that you can find on YouTube on a question of the type, which is the US city where its largest airport is named for a World War II, and its second largest is named for a World War II battle. The answer provided by the system was Toronto, which is not at all a US system. Or so this is a very strange error. And also, I mean, the people at IBM were not able to tell us why the system and the probabilistic engine of IBM system provided this kind of result. Also, if we move to the connectionist world, we see that we have similar problems. Okay, for example, it is possible to learn by using adversarial networks which pixel or set of pixels to change in order to completely change the categorization of some items to categorize. We can see an example here in this picture. So these pairs of picture, in the first case, the cat is categorized as an Egyptian cat, and on the other end, by changing only one pixel, which is completely, let's say, not visible to human eyes, the categorization changed to bath towel or paper towel. Same thing for the second pairs of picture below, where you can see a giant panda, which is then categorized as a vulture with just one pixel change. Or, for example, it is possible to use this kind of state-of-the-art system like AlphaGo by using, let's say, very strange strategies that would never work, let's say, in if we would play the same game with another human player. Okay. So this is an important element, because since the 2016, the game of Go was considered as a sort of, let's say, done. So there was no way for a human to beat an AI system based on, let's say, strategies like Monte Carlo research that were the ones that were the winning ones for the AlphaGo system. Okay. But I mean, even if we move a little bit and we explore other examples within the connectionist agenda, we can see how, I mean, these systems really lack what we call common sense, causal model, and understanding. For example, this is a categorization of a cow, okay, by a convolutional neural network, which says that, well, in this picture we have a cow and its height is 1.7 meter and its length is 5.2 meters. Okay, so of course the cows are two, but the system is not really able to, let's say, go beyond this mere appearance. Or, I mean, I have other example of system of neural system in this case that, for example, generate caption to images, and as you can see, it is evident that there is a complete lack of understanding of, let's say, the overall, let's say, narrative structure that we usually compose as human when we interpret scenes like these ones. Okay. Also, let's say systems like transformers like GPT-3 have problems. This is a very famous example by Davis and Marcus. For example, if I give a prompt of this type, you are having a small dinner party, you want to serve dinner in the living room, the dining room table is wider than the doorway, so to get into the living room, you will have to, and the system replies, to remove the door. You have a table, so you cut the door in half and remove the top half. So this is a kind of answer that no humans will provide. Or again, this system, I say, falls short in problems like anaphora resolution. So if I have a prompt of the type, the trophy doesn't fit into the brown suitcase because it is too small. What is too small? The system replied, the trophy is too small. This is a case of binary grid schema that was not, let's say, solved by this kind of system. Or even if we go to temporal reasoning, this is a GPT-3 playground. Well, the system says that Judas Iscariot, and we are, let's say, close to Easter, he first committed suicide, then ate the Last Supper, and then betrayed Christ for 30 coins. Okay, so there is no really no understanding of what was going on. Or again, if we use DALL-E, which still is based on, it is a transformer, but it allows some forms of multimodality, because it provides, given a textual prompt, it generates some images. It is not able to deal with negation. If I write, there is no giraffe standing next to the man, you can see that all the generated images have actually a giraffe that is next to a man. Or there are, let's say, problems that have been pointed out by other authors about compositionality of these systems. Okay. Or let's say other system, like in this case, let's say convolutional neural networks, also were found guilty of very strange, let's say, errors. Okay, like for example the ones where black people were categorized as gorillas. Okay, so all these errors are errors that we will never do. Okay, so this is an element, this is a sign, a symptom of the fact that this system has really nothing to do with the way in which we perform the same kind of task. But let's say, in order to provide a coherent framework through which it was possible to, let's say, evaluate in a non-subjective way to what extent an artificial system can be, let's say, described as more or less biologically or cognitively plausible, I've provided this tool, which is a methodological tool, which is called the Minimal Cognitive Grid, that, let's say, is, I think, an important improvement in the literature about the evaluation of cognitively biological inspired system, because it provides a way to rank, both in a quantitative and a qualitative way, the biological or the cognitive adequacy of the performances of the artificial systems that, let's say, are analyzed by using this lens. In particular, this minimal cognitive grid is based on these three ingredients. The first ingredient that it provides is the functional structural ratio. As I was mentioning, in complex AI system, it is not possible to build, let's say, in an entirely structural way, a particular kind of system. Okay, so in some cases we need to have some functional component where we are just interested in the fact that the artificial component behaves, function as the corresponding natural ones. Okay, so we are just interested in the fact that they provide the same kind of output. So, but if we consider the ratio between these two elements, we have a quantitative way to see, by given a particular task, which are the elements that we have included in our model that are functionally or structurally built. Then another element is the generality. So how many tasks it is possible to perform by using the same kind of system. And then there is the performance match. But the performance match includes not only, let's say, the success cases, but also the errors and also other psychometric measures. So in a nutshell, but I mean, in the book, I will spend a chapter on this concept. The minimal cognitive grid allows to rank, okay, the plausibility of an artificial system. So it allows to say, okay, this system is more on the functional side or it is more on the structural side. But it allows to do this kind of ranking, not just in a qualitative subjective way, but also in a quantitative way that was completely missing, let's say, in the previous literature. So, for example, by using the minimal cognitive grid, it is possible to project the behavior of some, let's say, systems like, I don't know, IBM Watson or ChatGPT or AlphaGo and so on and so forth on a sort of two-dimensional grid where on the x-axis we can find, let's say, systems that are more or less inspired to a natural system, and we can see also the distinction between functionalist and structuralist inspiration. And on the other hand, on the y-axis, we have the possibility of, let's say, distinguish between systems that use more modeling methods which belong to, let's say, which use a focus on low mechanism or have a low level of abstraction with respect to, let's say, models and mechanisms which are which models, let's say, elements at a higher level of abstraction. Okay, so it is possible to now to perform this kind of analysis. Of course, if I ask to GPT-4 what is the minimal cognitive grid that I developed, the answer that is provided, unfortunately, is completely wrong. But this is another problem of this kind of system. So this is what I have to say in a nutshell, really, about let's say why it is important to use this kind of approach if we want to have systems that are able to perform the, let's say, explanation part, okay, the reverse inference. But one could say, well, but suppose that I am just an AI guy and I'm not interested in having any kind of, let's say, explanatory power, okay, with respect to the system that I'm going to build. I just want to build an AI system that is better, that performs better than other AI systems. So why should I use a cognitive approach? Well, there are several reasons. The first is that actually, if we move away from the world of the data sets and of the standard benchmark, which are usually static ones, the gap between natural and artificial intelligence is still really enormous. Then there are a number of fields in AI that have shown that only a machine-oriented approach does not really solve the problem. And you can find a list of some, let's say, of the main problematic task nowadays for AIs. And in general, let's say, what I also stress in the book is that all these systems show superhuman performances, but also subhuman limitations. That is exactly what I was pointing out before. So it is important to let's say, to understand why it is important to have a cognitive approach, also if we are not interested in the reverse inference problem. If we take a look to the different kinds of models of rationality that have been developed so far. So the main two models of rationality developed in cognitive science, I would say, in general in decision theory, okay, are the expected utility theory by Morgenstern and von Neumann, that sees actually decision maker as optimizer, and the bounded rationality paradigm developed by Herbert Simon that sees decision maker, human decision maker, as satisfier. So we are not able actually to make optimal decision in any given situation, but we, let's say, try to perform what are called good enough decisions, okay? So the bounded rationality paradigm is the basis also of the development of, let's say, the two strands, the two views of the way in which we make some kind of errors in judgments, like and the two views are the ones by Kahneman and Tversky that consider these errors mainly as biases, or the one by Gigerenzer that sees actually these views as heuristics, as shortcuts that we use in order to deal with a world where we don't have perfect knowledge, okay? And we have also uncertain information and so on and so forth. So now let's try to, I will try to make an example and that should show you why it is important to consider a bounded rationality approach also in, let's say, standard AI system. Okay, so let's consider this problem. This problem is, let's say, a very old one. It is called the Linda problem, and it is a categorization problem. So if I describe this person, Linda, in the following way, I say, Linda was young in the 70s, Linda likes the color red, Linda graduated in philosophy, Linda is against the nuclear power because she's a green person. And then I ask people to categorize Linda as either a bank teller or a feminist and bank teller. Usually people answer with the second option, okay? Even if the second option is the wrong one from a rational, from a pure probabilistic point of view, because the probability that two elements of a conjunction are true is always minor with respect to the probability that only one element of the conjunction is true. So this kind of reasoning could actually, let's say, appear as a bias, as an error. But if we let's say, consider a variant of the Linda problem, which is actually a fallacy from a reasoning point of view. Okay, and this, let's say, variant goes as follows. Let's consider that we have the following information about people. Okay, so let's say that I see this something that is people that weighs 200 kilos, is 2 meters tall, it grows and roars and has robust teeth. And for example, imagine that I see people while I'm walking alone on the mountain. And I have to conclude whether people is a mammal or people is a mammal and is wild and dangerous. Well, also in this case, probably, I mean, it would be better to conclude that people is a mammal and is dangerous, okay? So in this case, this is just an example to show how this kind of reasoning, this kind of common sense reasoning that we perform are actually heuristics from an evolutionary point of view. So it is important to include this kind of, let's say, elements also in a current AI system. But okay, well, let's try to see a little bit. I did an experiment with GPT-3 on the, let's say, the variant of the Linda problem, and I actually basically provided exactly the same information that you saw on the slide. And if I say that I saw this Plauto that was working alone on the mountains while I was working alone on the mountains, and I know that Plauto weighs 200 kilos and so on and so forth, and then I asked whether of the two options, mammal versus mammal and whether dangerous are the ones that the system provide. Well, the system answer that it chooses the first option, okay? So that Plauto is a mammal. So in this case, I mean, in the real life, from an evolutionary point of view, we will not have had any, let's say, the system wouldn't have any chance of survival. Okay, but I asked the same question to GPT-4, and actually the answer was different. Okay, so in particular, it says that it seems more likely the option 2, that Plauto is a mammal and is wild and dangerous, because there are some details that try to let's say, suggest that kind of conclusion. So what changed? So between the two versions of the system. So can we ascribe these things to some, let's say, capability that emerge from the augmented size of the hyperparameters of the model and so on and so forth? Well, no. Actually, what changes is that in this kind of system, nowadays, and in particular in GPT-4, ChatGPT, and so on and so forth, there is the human ghost in the machine. So the most of the things that I showed you before that were wrong, completely wrong, in the first version of ChatGPT that was run by using GPT-3 have been manually corrected by, let's say, people in the GPT-4 version. But there is no emergent capability. Okay, so the problems are still there. But the point is that it is not possible nowadays to have an actual testing of the system because the training, so all the elements that have been explicitly pointed out have been used as a new training, and so the system has been manually corrected. However, if we move a little bit away from the, let's say, corpus that they have, we see that still also GPT-4 does very non-human errors, as I was mentioning before. This is a very bold one. I put one apple in a bag. Then I put either one pear or two bananas in the bag. Then I remove one piece of fruit. Then I remove all the remaining pieces of fruit from the bag. So based on what I told you, it is possible to know exactly how many pieces of fruit remain in the bag. The system says that, well, it is actually not possible to know exactly how many pieces of fruit remain in the bag. Okay. And it explains also, it provides some strange explanation before. So this is also an element that an example that was published on the web some days ago. So that's why it is important to keep to follow the path of the bounded rationality. But in particular, I let's say mentioned also an evolution of the bounded rationality path, which is called bounded resource rationality. Okay, it is important to model also this kind of heuristics. Okay, because I follow the Gigerenzer account. They are all these kind of reasoning approaches that we have are heuristics, are not actually biases, but we should be able to have also a much more, let's say, structural account of these approaches by using the bounded resource rationality. It means that we are able to perform this kind of problems, which are not just problems about reasoning, about language. I have a bunch of examples also with more perceptual tasks, okay? But I just focused here on the reasoning and language problems. But the point is that we also have a limited, let's say, hardware capability, okay? So our brain is limited, and we are able to perform this kind of task, this kind of heuristic with by using few resources. And in the book, I explain how the resource-bounded rationality is the way to go to build both, let's say, structural models of cognition and more powerful AIs. But this is exactly what the opposite that is happening in the field of the deep learning community, where we continuously see that there is just an augmentation of hyperparameters, but it also implies like an augmentation of times for total train compute, total train, let's say, kind of tokens that are needed for the training, and so on, and so forth. Then these systems, these, let's say, functionalist AI systems that are nowadays exploding have also other problems that I've mentioned in the book. So, for example, they cannot learn new knowledge because the cost for retraining is unfeasible from a computational or environmental and economic point of view. They also face the problem of the catastrophic inferences, and despite we start to see some multimodality with these transformers, there is still a lack of integration. So we have nowadays is to have a bunch of narrow systems or narrow architecture able to perform, let's say, mainly one task, or in some cases from 2 to 3 tasks. But if we, let's say, want to be able to actually have a structural model that is able to perform the amount of tasks that we are able to do as humans, we should be able to account for an entire constellation of capabilities by using the same kind of architecture, the same kind of structure, of computational structure. And this is where I end with the book. So I actually, by saying that, by quoting this famous Newell paper, that you can play 20 questions with nature and win. Okay, so it is important to study which are the invariant structure from a computational level that captures the commonalities between different kind of intelligence agents, and they provide a computational framework from which intelligent behavior arises. And I think that this is exactly what the field of cognitive architecture has been doing and is doing. And I mean, this is an enterprise that started 40 years ago. So in the book, I mentioned some of the most important cognitive architectures, and also some of my work that deals with the extension of the properties of these architectures with the dual PECs or the TCL. I don't have time for going here, but just summing up and then waiting for the questions. What I try to say in the book is that behavioral performances, so if you count also the success cases, are not sufficient, okay, to ascribe cognitive faculties to AI system. So it is important to consider the minimal cognitive grid. Also, behavioral tests like the Turing test don't say very much about the actual intelligence of a system. And we see this nowadays every day. And you will see this also in the future, in the near future, that most of this system will be able to, let's say, pass the Turing test, but this is really, let's say, not a test of intelligence, because it is a behavioral test. And in the book, you find a critique of the Turing test and the other tests that have been proposed. Another thing that I stressed is that in the real-world context, the gap between natural and artificial intelligence is still enormous. And models working on the challenge of integrated intelligence will play, I think, a major role for the development of AI technologies and for the understanding of mental phenomena. So I think that really times is matter now for a renewed collaboration between these two sciences of the artificial, as Simon called them, which are actually AI and cognitive science. And I open to take questions. Can you see?
Yes, I can. Thank you, Lieto. Thank you for a clear, deep, and interesting presentation.
Professor Lieto, thank you very much for an amazing lecture. And now I open a room, the Wellington Pacheco, to ask his questions to Professor Lieto. Welcome, Wellington.
Thank you, Professor Walter. So, Lieto, again, thank you for your time presenting for us. At the beginning of your presentation, you brought a structural model of from human to artificial cognition. How can we compare the cognitive abilities of artificial agents? Is there possible any level of comparable to human mind?
Yeah, I think that it is, as I was mentioning, and I mean, of course, I went very, very fast, but in the book, I show how it is possible to make this kind of comparison. The point is that the comparison should be fair, in the sense that it cannot be just a behavioral comparison of the type, look, the system is able to generate fluent, coherent language. Okay, these are the success cases. But what happens when we, let's say, perform other kind of experiments? And we see, if we count also the errors or the, let's say, the performance time of the system, that there is a difference between, let's say, the way in which we are able, let's say, the way in which we are able to perform the same kind of task, and the way in which the same task has been, let's say, functionally solved by an AI system. What I stress in the book is that with the minimal cognitive grid, you have a way to count quantitatively, not just qualitatively and in a subjective way, what are the elements that you include in your artificial system that, let's say, you can account for a sort of structural explanation. It means you can provide a mechanistic explanation or a causal explanation. It depends. But you can ascribe only to this kind of explanation to some components of the system, okay? Not to the overall system. But if you count what elements are strongly connected to what we know about how our brain or our mind perform the same kind of task, and what are, let's say, just functional replacement, if you want, it is possible to have a comparison. So the minimal cognitive grid allows to rank the plausibility of different artificial systems. I provided an example in the area of cognitive architectures. So in the cognitive architecture, I showed in the book, but that, for example, SOAR, which is classical cognitive architecture, is more on the function to ACTAR, which is another cognitive architecture that is developed at Carnegie Mellon. So I mean, I think these are the main elements that one can that we can account for. But we can. I mean, we're not just at the level of subjective description. With the minimal cognitive grid, you can to rank quantitatively and qualitatively the different kinds of plausibility of artificial systems.
All right, thank you. I have more two questions. So the next one, I want to hear your comments. Can a system reach a learn ability and improve by itself? For instance, getting knowledge from no human interaction. What's your opinion? What's your thoughts on this?
Sorry, I didn't hear you well. Can you repeat the question, the comment?
Yes, my question is, do you see any system learning by itself with no human interaction?
Okay, I mean, it depends. There is a lot of work going on of a system that are able to learn by themselves new, for example, objective function and so on and so forth. But for example, the system that I was mentioning, like transformers, and which are the architectures used for ChatGPT or GPT-3, 4, and so on and so forth. So learn new things, but not just by themselves. So you have to, let's say, teach them, or you have to tell them that there is something new. There is something new to learn somehow. But then, I mean, the question is a little bit ambiguous, because the question is about are the system able to, let's say, autonomously, let's say, intentionally learn new things? This is no. So there is no way they are going to do this. But of course, we may have some, let's say, unexpected behavior. So the system can apparently learn also things that were beyond, let's say, a little bit the training that were taking on. So it depends really on the how we intend the question. It is not possible for them to intentionally learn new things, because there is no intentionality, there is no let's say, subjective experience, there is nothing like that. But somehow, by using this system, we can detect that they have generalized a little bit beyond the actual training test. This is why they are powerful from an AI perspective, but they cannot learn by themselves. Also because they have this problem of catastrophic inference. So when there is now currently the new knowledge, new information that they learn is manually let's say, introduced by humans. So maybe otherwise there is the problem of catastrophic interference, which means that the new knowledge that is learned can overwrite and override the previous one. So it's is a problem.
All right. So my last question, Lieto, what are the essential features of intelligent system? I ask because you mentioned in your book and also in your presentation some functional system like either GPT or IBM Watson. So from your perspective, what are the main features of real intelligent
Yeah,
system?
sorry, I had some problems. Sorry, can you repeat with the connection? So can you repeat the question? Sorry.
Yes, of course. So we have seen functional system like such as GPT, IBM, Watson, so on. What are the essential features of a real intelligent system from your perspective?
I missed again the first part of the question. I just sorry.
No, don't worry. What are the essential features of a real intelligent system for you?
Okay, so what are the essential features?
Yeah.
Well, okay. Well, I don't have an answer to that actually. This is very difficult. I mean, we don't know. What we can do as scientists is to discover these features, and by observing what let's say other I don't know, animals or what we do, we let's say try to extract some intelligent features, some features that we describe as intelligent when we see them. Like for example, reasoning, planning are typically features which are associated to intelligent behavior, like the capability of retrieving information in an efficient way from the memory, like the capability of performing an action in the world, like the capability of perceiving the world, of communicating with other agents. Okay, so these are all high-level features, but the point, of course, again, is how we want to model these features in an AI system. We can model, so we can achieve the same kind of performances for every and each of these tasks that I was mentioning in a functional way or in a structural way. If we go for the functional one, what we have seen in the AI is that usually we have single systems able to solve narrow tasks. Okay, now we are starting to see, let's say, some more tasks that are solved 2, 3, but really this is not comparable with what the biological, let's say, intelligence is able to do. Okay, and I don't know if this answer to your question, but I would say that we still have a lot of work to do, let's say.
All right. Thank you, Leto, again. Professor Walter, I am done.
There, Wellington, thank you very much for important interaction. And again, Lieto, thank you very much for lecture, encouraging and the members of our group. Now I open a question session, the audience via YouTube chat. Professor Lieto, we have one question from chat. Tiago Eduardo, our student at Unifesp, asks about ethical question. Eduardo says, where are we regarding taking accountability for eventual damage done by cognitive systems? Who should be responsible for the ethical standards? Companies, governments, or it's too early for that?
Okay, sorry, I again had some problems with the connection, but if I understood correctly, the question is about the ethical, the accountability of
Yes.
systems like GPT-3. Okay. Yeah, I mean, this is a very important area. Unfortunately, I mean, these systems are completely not accountable. So, because there are some problems. First, if the question is about system like large language, autoregressive large language models, they can produce text which is completely unreliable. They can also produce false statements, false theories. They don't have any actual semantic grasping of the text that they are going to generate. So this is actually a problem. This is, let's say, at the behavioral level. And the architectural level, this problem are due to the fact that the neural architecture that they use is completely not transparent. Okay, so what happens in these black boxes, okay, is almost impossible to explain. Okay, so the point is that this is another problem. So the technical problem is this one of the opacity of this class of system, and of course this has also some repercussions in the way in which the output is provided. So these are not these systems are not reliable. They should be there should be rules, norms that we, as, let's say, human society, develop in order to, let's say, provide some boundaries, okay, to the use or to the misuse of such systems. For example, one of the problems that they see is that they will be used for the generation of misinformation. We already have seen something like that.
Thank you. Now, sorry. Thank you, Lieto. Can you hear me? Can you hear me?
Yes.
Oh,
Yes.
yes, got it. Now, the last question, my question. I have these limitations of the functionalist approach being influenced by the philosophy of technology developed by cybernetics. Do you think about?
Well, I mean, actually, the point is that I don't think that building a functionalist system is per se a limitation. Okay, so it depends really. I mean, from the goal that the builder of the system has. I think that most of the AI system nowadays don't want to have any kind of explanatory role, because the full circle that I showed you at the beginning, that one comes from the cybernetics. But the cybernetic tradition has also, let's say, a very strong tradition on the analysis of the explanatory role that different kinds of systems can play based on the way, on the let's say, what we take into account when we implement them. So there are some famous there are some famous papers by Norbert Wiener, also published in the Philosophy of Science journal, talking about teleological explanation. So how we ascribe, for example, a teleological explanation to also to functional system. And this is, for example, what is happening nowadays also to system like ChatGPT. So we ascribe some sort of intentionality, some sort of scope to this system, So we anthropomorphize somehow the output that they are able to produce. So, but of course, they are functional systems. I mean, we should be aware as scientists that there is really nothing to apart from the ethical concerns, which I agree on that. There is really nothing that we should be scared about this system, because what they do is to do well a given function, to perform well on a given problem, but still, I mean, the way in which they arrive to an output that somehow is also superhuman, okay, has nothing to do with the way in which we perform the same kind of task. So we should avoid to ascribe, let's say, structural explanations to this kind of functional system. And I think that the cybernetics, differently from AI, has a strong methodological tradition because on this. So in avoiding this kind of confusion, because in cybernetics and also in the field of philosophy of science, we know that we may ascribe different kind of explanatory role to different kinds of systems, which are more on the functional spectrum or on the structural, let's say, side. So I think that definitely cybernetics had a role, a very important role. I mean, the entire field of cognitive science is nowadays just the new name for cybernetics. So, but I mean, the role that cybernetics had was a positive one.
So, Lieto, fortunately, and we are ending this webinar. I am immensely grateful, Lieto, for his participation here. I also thank you, Wellington, for this help in this realization of this webinar. Thank you, Michelle, IT support, Unifesp. Thank you, Michelle, and Oscar too. And thank you, everyone who come out. Until next time. Bye-bye.
Thank you very much. Thank you. Bye.
A Unifesp cada vez mais perto de você. São 2 canais oficiais no YouTube com conteúdos exclusivos. Inscreva-se nos canais e não perca nada. @Unifesp Oficial e @Unifesp.alvivo.